Okay, hello everyone. So in this video, we're going to try to prove that the language L, where L is a set of strings over an alphabet, and here, I should have specified, but here the alphabet should be 0, 1, that the language over the alphabet 0, 1, where all the strings in this language have more zeros than ones, we want to prove that this language is not regular. And so we could do this via the pumping lemma. So one option is via the pumping lemma. But what I'm going to do in this video is I'm going to use the closure properties. The closure properties. So in fact, it's actually going to be a 3-line proof if we use the closure properties. So how this is going to work is, let's just suppose that L is regular. Okay, so we suppose L is regular. Okay, and what we're going to do is we're going to try to apply some regular operations, right? So by regular operations, I just mean operations under which regular languages are closed, right? So let me just write that, regular operations, because this is not a standard term, is language operations, language operations under which regular languages are closed. Right, so for example, the intersection. If you have R1 is a regular language, intersect R2 is a regular language, this gives you another regular language. So the idea is we want to use a regular operation, or more than one, to create a new language that will conclude by the closure properties as regular when in fact we know that it isn't. And so what I'm going to do here is I'm actually going to take inspiration from one of the previous exercises we saw, where we proved, so you remember potentially, that we proved that 0 and 1, I think it was J, but let's use M. 0 and 1M, where n is strictly greater than m is greater or equal to 0, we proved that this language L prime was not regular. So for the purposes of this video, we're going to assume, because we've actually already proved it, that this is true, right? This is true that this language is not regular. And so the idea now is we want to somehow apply operations to the initial language L to get L prime. Okay, so how do we do that? Well, the language L contains strings that are in any order, right? So any number of zeros and ones, such that there's more zeros and ones, but the zeros and ones are in any order. And so to fix the order, right, to fix the order such that it's zeros followed by ones, I can use a regular expression, right? So 0 star, 1 star. This forces zeros to be followed by ones, right? And actually more specifically, it forces the pattern like you have zeros and then you have ones, and that's the end of your string, okay? So what we're going to do is we're going to take this regular expression, take the language denoted by this regular expression, and intersect it with L. And so what this does as a result is that what this intersection with some other language does is that it's going to filter L, right? So imagine L is this large language, right? So L is this big language over 0, 1, where for any string in that language, right? Any string in that language, the number of zeros is greater than the number of ones, right? Now what's going on is we're using this regular expression and this language to filter this space so that we only keep some of the strings. So we only keep this region, okay? And this region will be the strings that look like 0 and then 1, and also where the number of zeros is strictly greater than the number of ones. So in other words, strings that look like 0 and 0, 1 and 1, where n0 is strictly greater than n1. Well, this is exactly the language that we were looking for. This is exactly L prime, right? So this turns out to be exactly L prime, right? But because we assumed, right, because we assumed that L was regular and this language is regular, right? If we take a regular language and another regular language and we intersect those two, the output of that operation is also regular. That means that L prime is regular. But this is a contradiction, right? So we have a contradiction because in a previous video, in a previous exercise, we proved that actually the language L prime is not regular, okay? And so we have a contradiction, which must mean that our initial assumption was incorrect. And our initial assumption was that L was regular. And so that means that, right, this means that our initial assumption of L regular was incorrect, which means that L is not regular. And that proves this claim here. Okay, excellent.